right, welcome everyone. Welcome to session 4. We have a very exciting session planned for you here today. We have 4 ISS paper talks. We have an invited Kai talk as well. And just to remind you again, you can ask your questions in Discord in the appropriate channel there, and we will have all of the paper presentations first. And then we have a shared Q&A round. So every presenter will present for 7 minutes. And then afterwards, we will go through the questions and go through some exciting questions. So make sure that you ask your questions in Discord. So without further ado, I would like to introduce our first presentation here. Which is by Sigurdur Samuelsson, and he's going to talk about eliciting sketched expressions of command intentions in an IDE. So please, Sigurdur, the floor is yours.
Thank you very much for that introduction. All right, audio is good. Slides are showing.
Yeah, it's fine.
Perfect. All right. Again, thank you very much. Hi, my name is Sigurdur Samuelsson, and I'd like to present the results of an elicitation study examining how software developers would express commands in a software development environment by sketching right on top of the IDE. So sketches, that is, these informal ad hoc drawings, are a common way for engineers to express complex ideas. They are often created spontaneously with low cognitive effort to quickly express a vision of a solution while completing a larger task. Given that sketching is one of the most common ways for software developers to express their ideas, we were wondering why it is not used at all in one of their most central tools, the software development environment, or the IDE. Wouldn't it be convenient to express operations such as refactoring code by just simply sketching right on top of the IDE, much like annotating a document as shown in the picture? Exploring this vision is the long-term driver of our research. This question of could sketching be a viable, effective auxiliary command modality for software tools? And for an initial exploration of the potential of this vision, we examined 2 research questions. First, do different software engineers use sketching in similar ways to express commands? That is, do these users intuitively gravitate to some common approaches for sketching commands at all? And if they do, what are their preferred ways of expressing common commands? The results of this should tell us if the vision is worth pursuing at all, and inform our follow-up research with insights into actual user expectations, rather than just using our own assumptions of how this modality could work. So to answer our research question, we performed an elicitation study with 19 participants recruited from the Icelandic software industry. Participants were shown screenshots of an IDE on a pen-enabled laptop and were asked to imagine that this IDE that they were shown could interpret sketches and execute commands that these sketches described. They were then asked how they would express 16 different common operations by sketching. And those operations involve some code editing, some refactoring, some formatting, and some code comprehension tasks. In order to answer the first research question, that is to determine if different developers use sketching in similar ways to express certain tasks, we calculated agreement rates for our task prompts based on a method by Vobrock et al. To determine if sketches agreed, we classified them by style in which the participant had expressed the commands, parameters, and the selection. The detailed definition of the taxonomy and the observed breakdown of responses can be found in our paper. But as a brief example, consider the following 3 responses to prompt number 3, which asked the participants to move a method to a different line. So participant number 15 and 13 used a graphical approach for selecting the code block to be moved, and its destination. While the visual expressions are somewhat different on a stroke level, they use similar shapes for similar purposes. They are enclosing the block to be moved, and then pointing to the destination with an arrow. These sketches are therefore classified identically in our taxonomy, and the participants' responses are considered to be in agreement. In contrast to this, participant number 2 defined the scope of the selection with a sidebar and then expressed the command and the destination parameter textually. This response does not agree with the other two. Following this approach, we classified all responses and calculated all the agreement rates for all the prompts. The horizontal bar chart shows the results. A high agreement rate, as for prompt number 14, occurs when we observe a low number of classification groups, and there are preferably one dominant group, that is, one group of responses that are all classified identically. For example, as the stacked bar chart on the right shows, the responses for prompt number 14 fell into 3 groups, one of which contained 17 out of the 19 responses. Based on these results, we can then answer research question 1 positively. For 10 out of our 15 prompts, at least half of our participants sketched the envisioned command in a similar way. Looking at the responses for the dominant groups for these responses also helps us answer question number 2. That is, what are the actual preferred ways of expressing these commands? In our paper, we discussed the most common sketch expressions for all commands, and I'll just show 3 here for the sake of brevity. To move a call block, most participants encircled the code to be moved and then drew an arrow from the enclosure to the destination line. To add a comment, most participants drew a line to the desired insertion point and then prefixed the textual comment with a common symbol, such as the double slash for Java or even a hashtag for Python. To rename a variable, most participants struck through the variable and then wrote down the name next to it. Very reminiscent of grading a paper. Not all prompts yielded such straightforward responses, though, and participants were struggling with more complex and abstract operations, such as the following example. Prompt number 9 asked participants to sketch a command instructing the IDE to trace the source of a variable. That is, to show the code location where the variable is defined. We observed a couple of interesting approaches. For example, this one where the participant drew a magnifying glass icon inspecting the variable. Another participant drew a question mark on top of the variable name. However, many participants had a difficult time coming up with an appropriate sketch response, and several suggesting that making a long press gesture with a pen, saying that they wanted a context menu to appear where they could select the command from list. Our observations in this and similar prompts suggest that many users have an easier time sketching a command if everything that is affected by the command is visible on screen and can therefore be involved in the sketch in some way, as was the case with the previous examples. However, if a command involves some off-screen elements, users may have a harder time expressing it in a sketch since they can't visually refer to it in some of its elements. Although there may be some ways of expressing such commands through sketches, they don't seem to be as intuitive. We discussed the implications of these and other prompts that do not yield such clear expressions in the paper, and they give rise to a number of speculations that are worth examining more closely in future studies. And in conclusion, we found answers to both our research questions. First, we found that for two-thirds of our prompts, at least half of the participants sketched visually similar commands. This outcome is encouraging, as it shows that sketching as a modality in which some users intuitively express their intentions in similar ways, at least for some types of commands. Second, the high and the low agreement rate sketch expressions that we observed can serve as a starting point for future research on the human and technical aspects of sketch-based interaction, such as designing a visual command language, developing sketch interpreters, and conducting more in-depth user studies. And with that, I would like to thank you a lot for your attention, and I'm looking forward to answering your questions.
All right, thank you. I don't seem to be able to start. Oh, yeah, okay. Now I can start my video. All right. Thank you very much for this talk. So let's move on to the next talk. And this is Adam Williams from Colorado State University, who's going to talk about understanding gesture and speech multimodal interactions for manipulation tasks in augmented reality using unconstrained elicitation. So please, Adam, take it away. I also want to say Adam is looking for a summer internship, also announcing that. All right.
Thank you. Yeah, so I'm presenting work that we did at the Colorado State University on elicitation for augmented reality interactions using gesture, speech, and gesture and speech. So the goal of the experiment was really to observe how users would choose to interact in augmented reality and find themes and common behaviors. So to do this, we did a 3-condition elicitation experiment where we tested gesture and speech as a combined input modality, speech only and gesture only. Before starting the experiment, participants would do 1 practice referent in each modality and were shown video instructions. An important note for this is that the reference we used were animated, so no text was used. So in this case, for move right, we would render an object and then render it moving right over 2 seconds, and then have the participant sort of guess the interaction that would have triggered that, telling them that somebody had done it in another room. So during this experiment, we used 17 reference, which were translations on each axis, rotations about each axis, scaling, and then select, create, and destroy. Our research aims for the gesture condition were to find common hand poses, gesture reuse over reference, and common gestures. For common hand poses, we found most often the ones on the bottom left. And then for gestures, the translations were very consistently pushing the object based on the affordances of the object. Rotation gestures were mostly grabbing and rotating, although a few just used an index finger to indicate the rotation. Abstract gestures or indirect gestures came up more for abstract reference. So Bloom was used in a lot of different categories. This graph is used twice in this presentation. So this is the gestures for the gesture block only. The number of proposals is indicated by color. The reference are on the x-axis and the gestures proposed are on the y. So for Bloom, by looking at the row, we can see it was suggested by participants for create, delete, enlarge, select, and shrink, although it was mostly suggested for create. So we think, this Bloom might not have a clear mapping, but if we look at reference like move left and move right, there were only a couple of proposals and the responses were incredibly clustered to that 2 proposals. Another thing that can sort of be gained from looking at this is when you look at the columns, you can see sort of the space of proposals for each referent. So almost the level of disagreement between participants. When we switch to gesture and speech as a combined modality and look at the gestures, the proposal space sort of clustered more around the top proposals. So move left and move right went from having 2 relatively common proposals to having 1 really prominent proposal. For the speech, because we used animations, we felt that the speech results are not primed to repeat any text on the screen. So we were looking for the syntax as well as the utterances used. Most of the speech results are listed in the paper, but for the most part, for translations, people would just say move in the direction. So move up, move forward. Rotations would be rotate, but they would say rotate or spin and not an actual rotation in a direction. So it might say spin right, but that would be used for yaw and for pitch. And then for the abstract ones, because we used animations, participants had to guess what the actual referent was, which caused some difficulties for things like select, where we used a glowing animation and people would say highlight. But for create and delete, people came up with create, delete, and then appear and disappear relatively commonly. When we look at the syntax used for speech only, most people used action direction pairs. So again, move up. And a few people would just use action, which would just be move. When that transitioned to gesture and speech, people more often would use action alone. And this makes more sense when you're using a gesture, because then when you say move, you can give an indication of what you're actually intending the movement to be. Or again, with spin, people might then do the gesture that disambiguates whatever their command was meant. So for the gesture and speech, modality, we were looking at changes between the unimodal use and then the timing by phases of interaction. So for the timing, we measured when a gesture starts as the first visible movement of a participant's hand, and that's at 0 milliseconds. Stroke start, which was the first major movement outside of the preparation. So somebody would start moving their hand up and then go to point, and this transition was the stroke start. And speech start is when we heard an audible utterance being made. So the interesting part of our results here is that gestures precede speech most often, but more interestingly, the stroke, which is often the information content of the gesture, occurs incredibly closely to when the speech starts. So the information content of the gesture and of the speech occur around the same time. The stop information is just when the gesture stopped. I went through that really quickly. I'm sorry. I got nervous. But that was my presentation.
All right. Thanks so much. And again, yeah, this was a great talk as well. I just want to remind people as well to ask questions in Discord and post your questions there. Yeah, we can move on to the next talk. So this is a paper presented by Andy Wilson from Microsoft Research, and it is titled "Combating the Spread of Coronavirus by Modeling Fomites with Depth Cameras." Yeah, please, Andy, take it away. You're still muted, Andy, I think.
Sorry, you would think I would be up on this. Anyway, yes, I'd like to talk about a little project I have on combating the spread of coronavirus by modeling fomites with depth cameras. So early on in the epidemic, there was a focus on how the disease is spread by touching your face. Government officials told us, don't touch your face. Of course, this is easier said than done. Here I took some stills from a video that was put together by the Washington Post that showed that various government officials touching their face in the very same press event where they advised us to don't touch your face, right? So this is pretty amusing. It just demonstrates how difficult it is. So there are various technological solutions that have been proposed. So a number of the projects use smart watches and sensors such as accelerometers and proximity sensors to detect face touching. And perhaps most relevant to the present work is our computer vision-based approaches illustrated in the bottom right. This system uses a web camera and a machine learning approaches to detect when you touch your face. Now, early on in the epidemic, I did my own system using the Azure Connect depth camera. I don't know if you can hear the audio there, hopefully. This was something that was very easy to put together with the Azure Connect body tracking SDK, which gives you a 3D model, makes it easy to set a threshold on the distance between the head and hands. But there's more to this than face touching, right? Fomites are physical objects in the environment that, when contaminated, can transfer the disease to someone who touches them, such as elevator buttons, door handles. This is illustrated to great effect by a video made by Mark Rober. He's a YouTube personality. He found a particular powder that shows nicely in a black light and gave a bit of it to some school children at the beginning of their day. At the end of the day, Rober showed that the powder had spread throughout the room. So today we're still learning how COVID-19 spreads, but the discussion has moved on from face touching to wearing masks and social distancing. It seems likely that the virus can be spread through the air. However, CDC guidance still notes that COVID-19 may be spread by touching contaminated surfaces. In fact, very recently I saw an article describing how New Zealand officials traced a single infection to a wastebasket in an airport, and another was traced to an elevator button. So the contribution of this particular paper is a suite of techniques that leverage depth cameras to combat the spread of the virus. We extend the earlier Azure Connect-based demo that I just showed you to include detection of face touching and handshaking among multiple people, and we add modeling fomites of the physical environment. So here's an example of using the Azure Connect body tracking SDK in a more free walking around setting. And we can extend this to detect people shaking hands. So this is my son and I in the basement of my house. And there we go. So we can use multiple cameras to cover a larger area of the room and overcome some sightline limitations. And here we illustrate merging body tracking results. Red and blue body tracking results are from 2 cameras, and the purple color shows the merged results. We can detect when a tracked person touches the physical environment and create a history of where people touched. Here we test the head and hands and feet, against the 3D model of the room surfaces. And you can see the red indicates the area of the regions where I've touched. So this is implemented on the GPU and in what I call a scatter operation. We model the touch history as an image C. We compare the 3D position of each joint J against all 3D points in the physical environment, and then model the spread and uncertainty as a Gaussian distribution. The contamination map here, C, increases monotonically with time. So we explore a simplistic model of the virus spreading. We first show how joints can spread the virus by touching it. Contaminated joints are marked here in red. Note how the face joints are marked as contaminated when touched by the right hand, and then the left hand is contaminated when it touches the face. When the foot is contaminated, it then contaminates parts of the physical environment. Here the user begins with their left hand contaminated and then touches the back of the chair. The right hand then touches the back of the chair and is then marked as contaminated. So the virus can spread amongst various surfaces. So this is implemented as a gather operation that can be thought of as the reverse of the scatter operation. Summations here are difficult to do on the GPU, and we use MIP mapping to compute the sum over the entire image. And there's a bit more detail on how to do that in the paper. Finally, we can use projection mapping to illustrate the contamination map directly in the environment. This could provide some insight into how fomites evolve over time. We can also use projection mapping to illustrate when social distancing is violated. And in a moment, in the next part of the video, let's see, here the green shading is used when social distancing between these 2 people is violated. And then I'll show the next in the video, we'll see the social distancing calculations in the 3D graphics view. So, of course, there are a number of important limitations to this approach. First, as with any computer vision-based approach, camera sightlines can be a problem. We can't work with what we can't see. Second, touch precision is fairly low since we are not observing touch directly, but rather proximity. And this is something that we worked on elsewhere in the literature. Next, our prototype can't handle moving objects today. And some work would need to be done to have the contamination map update appropriately as objects move around the room. And then finally, the virus spreading model that I've outlined here is extremely naive and requires much more work and validation. There are a few considerations on how to apply the techniques in this paper. First is you have to ask yourself, is real-time audio feedback appropriate? And this depends on the application, like how many people there are in the room. Second, we might want to prevent touching rather than simply detect it. And this might be possible through clever processing of joint position information. Next, I believe that the system might be quite useful to monitor a space throughout the day. Give a HoloLens to the custodial staff so that they can see the contamination map directly and perform targeted cleaning. And finally, we note that the system can be thought of as a kind of fine-grained contact tracing, whereas we typically think of contact tracing as among individuals. This system could be used to trace who touched what in the physical environment. And so in conclusion, I presented a suite of techniques that leverage depth cameras to combat the spread of the COVID-19 virus. And I think an open question is how we can properly and safely validate this work. Thank you.
All right. Thank you for great talk. And let me play this again. All right, so this brings us to our next talk. So this is going to be presented by Yenting Ye, from the University of Waterloo, and they're going to talk about expanding side touch input on mobile phones, finger reachability, and two-dimensional taps and flicks using the index and thumb. So please take it away.
Thanks. Can you see my screen now?
Nope.
Not yet. Now we can.
Okay, cool. Thanks for the introduction. Hi, I'm Alan, and I'm going to present our paper expanding side touch input on mobile phones, finger reachability, and two-dimensional taps and flicks using index and thumb. This work was finished at University of Waterloo with Quentin, Anthony, and Dan. So we address the issue of mobile touch inputs, such as occlusion. The finger may block the content on the screen. Or due to the limited screen size, GUI widgets have to compete with the document of interest. Also, single-handed touch input vocabulary is limited, so researchers are still investigating new forms of phone input. One possible input area is using the side of phone. For interaction, Spelmanson extended power button into supporting 6 gestures. For sensing, Infinite Touch used a one-dimensional capacity sensor to detect touch input on 3 sides of phone. We combine and extend previous works by studying reachability around size and investigating a more expressive two-dimensional side input space. 2 application demos show the usage of two-dimensional taps and flicks. In the drawing application, a two-dimensional side tap command menu is demonstrated. Flick toward upper or lower edge can open or close the menu. Commands are arranged corresponding to the side position and edges. Tap on the different location can select the color and stroke weight of the brush. In the map application, we show how taps and flicks could be combined. Flick along the edge zoom the map in or out. Different edge indicating to different zoom speed. Tapping on the upper edge recenters the view to predefined location. Different position along the edge can be a different city. 3 experiments were conducted. The goal of the first side reachability study is to understand the preference and ability to reach sides of a phone. 18 participants were recruited and all 5 fingers were tested. The image showed 3 phone mockup and 16 side locations around the phone that we tested. 2 measures were collected in this study. For the preference score, participants rated from 1 to 7. In addition, they can give 0, indicating they cannot reach that location. And we use computer vision method to calculate the grip stability metric from the initial and reaching grip images. Here shows the side reachability results of preference and grip stability by location and phone size for thumb, index, and the best score across other 3 fingers. As the results show, all locations can be comfortably reached. However, the bottom side is least comfortable and should be used only for infrequent functions. Thumb and index finger can reach most side locations, especially the middle to top right for the thumb and the top left for the index finger. We then use these areas for the following experiments. To make our result accessible to designers, we created an interactive reachability viewer showing interpolated measures for each finger on any device size between our small and large mockups. Designers can hover to view the scores, select measures, fingers, and phone size to check the corresponding results. Then we conduct a side tapping experiment to investigate thumb and index 2D side tap performance. We asked 12 participants to tap 3 edges and 8 positions with their thumb and index finger. Figures show the task location and experiment interface. We combine the capacitive sensing with the motion tracking system to simulate touch event on the side of phone. Our pilot test found touching the upper edge with the index finger was difficult, so only the lower edge and middle are tested for index. Here shows the performance and preference rating for side tapping results. Overall, thumb tapping is more accurate and more preferred than the index. It may due to greater dexterity with the thumb. When using the thumb, the upper and lower edge were more accurate. This is likely due to tactile feedback on the edge. Midway side positions were preferred since they closer to the rest positions. When using the index, middle edge was difficult to reach and less comfortable. Therefore, one-dimensional side input may be more suited for the index finger. The third experiment investigated side flicking gesture with thumb. We test the flicking gestures, which are short and fast dragging actions. 12 participants were recruited. We asked them to perform the flicking gesture for both types, along edge and across edge, and in both directions, abduction and adduction. For the along edge flicking, 3 edges and 3 positions were tested. And for the across edge flicking, we only tested in 3 positions. Here shows the task and the experiment interface. Following figures show the result of side flicking. For along edge flicks, all gestures were rated above nature. However, the bottom locations were rated lower, likely because the thumb needs to be bended to reach bottom positions. For across edge flicks, abduction flicks have higher scores since it's more steady than the other direction. We summarize some design recommendations for 2-dimensional side input. First, middle to top location are preferred since the bottom part of the device is usually used for grasping. Second, due to the dexterity and the familiarity, thumb should always be prioritized. Third, taps are generally faster and more appropriate than flicks. Last, a faceted side shape is better for 2-dimensional input due to the edge tactile. We then created a full 2-dimensional side touch sensing prototype to illustrate the potential of side input. It uses 3 custom PCBs, each with a capacitive sensor to detect the touch events. In conclusion, our work showed that every location around the phone can be comfortably reached, and side touch input can be expanded into 2-dimensional taps and flicks. Especially side input with thumb has great potential. And please see the paper for more detail, and I'm happy to answer the question after.
All right, thank you very much. All right. We can just to remind people again, like please add your questions to Discord, and then we can move on to the next talk. And the next one is going to be presented by Sohail Kianzad from the University of British Columbia. And the paper is called Fasking on Paper, Accessing a Continuum of Physically Assisted Sketching. So please, Sohail, take it away.
Okay. Thank you, Joe, for the nice introduction. Hello, my name is Sohail Kianzad. I'm a 4th-year PhD student at Computer Science Department, University of British Columbia. And can you hear me well? Okay.
Yes, we can hear you perfectly.
Okay, sorry. And I'm glad to present our work on behalf of Spin Group and with the title of Fasking on Paper, Accessing a Continuum of Physically Assisted Sketching. I'll start with the conceptual framework of fasking, which highlights a fluid transition from assisted sketching to freehand drawing using 2 different types of constraint. And then I will explain our force feedback device capable of implementing this framework. The fasking pen, unlike other physical assisted drawing tools, uses an untethered ballpoint drive mechanism, which produces force by driving a contact ball over a surface. Friction between the ball and the surface provides a ground back to the user's hand. Using haptic constraint, fasking pen can support computer-assisted sketching and potentially improves users' quality of drawing. What is the need for such a device? If you happen to walk by an art supply store, you'll see a different world, full of brushes, pens, papers, and so on. A world which is different than graphic and digital art, the world of physical drawing. Physical drawing, either on paper, canvas, or large surfaces such as wall, is highly valued because of originality, authorship, personal narrative aspects, and continuity of expression. The freedom and functional control afforded by physical drawing is unmatched in electronic media. Paper sketching, however, lacks digital enhancements that we can see in CAD softwares, and it's laborious to move fluidly between paper and digital media. We consider different use case scenarios where we believe that a computer assistant can help users with hand drawing. The first example was learning to sketch. Learners could be novices, hobbyists, or people with physical stroke that all might be benefited from a physical assistant to draw a straight line, keeping the proportions right. For example, to draw the face of the bear, or putting drawing objects in perspective. Another example was rapid technical sketching. Rapid sketching is a fast and flexible method of communicating ideas visually. So this could be mainly for architects who are brainstorming with their clients early on in their design process. Using traditional drawing tools, it's very difficult to keep the proportions right. Also, scaling and orienting geometries requires time and effort. Another example is large-scale drawings, which might use different physical aid and drawing tools than conventional tools that we are using. For example, to draw a straight line or smooth curvatures, a designer might use tape drawing. All that said, we introduced the FastSkin framework, which provides a fluid transition of control sharing from assistant to freehand drawing, making use of different types of constraint. In active constraint, a force field draws the users in a particular direction or a rate and requires active force feedback. It always entails active guidance. In passive constraint, movement is free up to a boundary, then a constraint. A binary boundary could be implemented via passive device or a break, because it's just preventing the users from going somewhere. Here, y-axis denotes the strength of the constraint. FastSkin can fluidly access all points of this axis by bearing down to the pen tip while drawing. So the core interactions of FastSkin includes constraint, which have already been explored in the literature. So we have bound constraints, which prevents users from going, and bring constraints, which drag users to certain points at certain speed. We also introduce control sharing. This control sharing will give the control to the users about the amount of assistance they want to get from the system. This is different from adaptive control, where the computer decides on the amount of control. We just give this authority back to the users. We implemented a FastSkin pen, which consists of 4 main parts. We have a digital pen, which provides us with the absolute position sensing and pressure sensor. It has a processing core, which is basically a Raspberry Pi. We have orientation sensors and a ballpoint drive. You can see on the bottom right of here that 2 pairs of motors are rolling the ball in 2 different directions. We have done several iterations on our ballpoint drive to make the back drivability and speed and force in the right shape. Also, we created in order to create some functions, we created a lightweight CAD software using PyQt on our Raspberry Pi. So the whole system is standalone. It can bring 7 different functions based on our core interactions that I explained earlier. And there is also a perspective options that can apply to the rest of these. So here you can see on the left, there is a paper palette in which users can select just by clicking on this paper palette, and then they can draw it on the paper. Control sharing is also a super important part of our system. It provides all the advantages of collaborative drawing. It provides fast and accurate drawing, while it preserves the expressions of the users and also reduce the needs for visual involvement. On the left, we can see that the device is guiding users to draw a circle. This is coming from a drawing of a circle by one of our participants. On the right, however, the users can violate these guides. So the color coding of this graph shows the pressure profile. The yellow means that the user is taking control by pressing down, so it can violate, and the blue means that the system is taking control and drive the users to draw a circle. Please visit our paper to learn more about our technical evaluation and user study results. Okay, in general and conclusion, we find out that our prototype was sufficient to assess fasting potentials. The concepts found enthusiastic perceptions by our participants, as well as we got some feedback points to improve our system. In future, we are planning to implement some other functions, including precise, rotate, amend, as well as copy, paste. And we believe that it's a small, straightforward step to full digital twinning. Modify it on a screen, and then bring it back to the users with guide tracing. Thank you so much for your attention and time, and looking forward to your questions.
All right, thank you so much. This was a great talk as well. And I forgot to mention this was an invited Kai paper, so thanks so much for being here. Sahil, this was really great. All right, so that brings us to the end of the presentation part of this session. So now we'll go back into the question rounds. So I'll ask the presenters to put their turn on their videos so that we can see each of you, and I'll go through a few of the questions that came up. So I'll start with Sigurdur with the first paper. So there was a question about your gesture study. So did you about the gestures that you looked at. So did you identify any similarity or difference between your gestures and manual annotations that developers added on their documented code?
Well, with gestures, we're not really looking at gestures themselves. We try to exclude them as much as possible, such as touch gestures. We really focused on sketching as the input modality. And with that, there was an annotation that was kind of the thought we had. With according to annotation, we are writing our own software to allow the developers to do this. That is in the development stage right now, and that does involve allowing the users or developers to switch between ink types. One of them which does not execute command, but instead just allows them to annotate, and that saves the state. So people can annotate documents, code really, while the other type of ink will be interpreted, first recognized and then interpreted into commands if they are interpretable. I guess that kind of tries to answer the question. We try to veer off being gesture-based because that is not really what we're looking at. So like, long press gestures and such.
Yeah, thanks for your answer there. So I forgot to mention this was a question by John van der Donk. I'm sure there can be more discussion on Discord afterwards as well. I actually have just a quick follow-up question for you as well. I was wondering what device modality you were thinking about for this. Would this be like mostly on a touch-based big whiteboard? Would this be a tablet? Would this be a touch-based laptop?
Yeah. We recently got a device that we can test this on, which is a very large interactive display. The main modality for this, and this is also determined in the paper, is the meeting room, where we have the code reviews, where you have the design meetings, where you have multiple developers at the same time, coming up with new features, doing these code reviews, and more and more frequently they are becoming interactive in the fact that they are not just using a projector, but they're using actual touch display. And the idea here is that instead of switching between talking about the code, if, for example, during a code review or during feature development, one person kind of leading the discussion is at the table, drawing some annotations and such. Instead of going from that and then starting to go back to the mouse and keyboard to maybe, let's say, create a template function that they're going to implement later, or adding comments to the code, or refactoring something that they needed to refactor. Instead of going back and then switching from that thought process of like designing back into now we have a mouse and keyboard, you can immediately do that in the same modality you're already in. You were annotating, now you can switch from annotating to actually commanding, and then you can do these different sketches to do refactorings that are available. For example, extracting methods, adding template code, adding actual comments that then can be implemented later.
All right, thanks so much. Next, we have some questions for Adam. There were some questions about your study method. Joe van den Donk was asking if you allowed people to elicit the gestures several times, and if not, how did you guarantee that the elicited proposal remains unique?
We did not guarantee that the elicited proposal remains unique. For most cases, we got unique gestures for each referent. But from that one side with the purple images, there was a lot of gesture reuse, and this was also within participant, but we were interested in looking at how people would choose to reuse gestures. It seems like most elicitation studies kind of tell people to generate one and then not use it again, which is totally valid, but we were trying to examine it in a little bit more like arching themes of gesture use.
All right, perfect, thanks. And just another quick question. There was also a question of whether you have thought about other modalities in conjunction with hand gestures, like feet interaction, for instance.
We have. We're not so much with feet, although just because we think people might be seated when they're working on AR, but feet are pretty valid inputs. We're going to look at gaze and some more traditional input methods like a keyboard in conjunction with headset and see how that changes interactions.
All right, perfect. And here was just another quick question. Did you also look at recall of the gestures?
We did not look at recall.
Okay, perfect. All right, there's also some questions for our third presentation, some questions for Andy Wilson. There's a question from Joachim George about what approach you use to merge skeletons from multiple connects and what the precision is for that.
Well, yeah, the approach is really just a very simple greedy matching where we match up in a kind of robust fashion and then average the joint positions. There's nothing particularly novel about what we did there. As far as precision goes, I think we're at the mercy of the Azure Connect body tracking SDK. And so I don't have good figures for you on joint position precision for the Azure Connect body tracking SDK, unfortunately. So, all the body tracking things, you're really just kind of using what's available. The Connect SDK could also be used. I think I find the Connect, the Azure Connect body tracking SDK to be a little bit better. There's quite a bit of evolution in how that system works.
All right, thanks. Another question, and it's a bit related to that, was by Bernardo Marquez, and he was asking, like, if you would do this in a scenario like at an airport, for instance, a really large space, how many skeletons could be supported at once? Do you have an idea how that would work for a larger scenario?
Yeah, that's a good question. I haven't had the opportunity to really face into a really large deployment. It would be interesting to consider even without sort of going into it. But within each camera, I'm not aware of any particular limit in terms of the number of skeletons that can be tracked in the newer body tracking SDK. I think you're probably going to run out of physical space before you run out of skeletons as they're tracked. And then the other question is, like, how many cameras can you mount into space? And that's a good one, because the calibration procedure is, has this kind of quadratic relationship in terms of the computation, because they each have to sort of cite each other. And so today there's no real consideration for, for very large N. The biggest network I've done so far is 8 cameras, 8 projectors and 8 cameras. And so that's not going to be enough to cover an airport, obviously. So I think that's a really interesting question. I think I don't have great answers for that, but my guess is there's plenty of optimizations and beam search kinds of techniques that one could get running in this setting.
All right. And a final question from Catarina Fidalgo was about privacy issues. Have you thought about that at this point, or any insights on that? Yeah,
that's a really good one. I think overall, I think we have that question, pertains to sort of any system that uses cameras. I think in this case, things are maybe a little bit better, maybe in the sense that we're not using the color camera on the, we're not using real just imagery. We're using the depth images and then the skeletal tracking results. And so, you could argue that one way or the other that that's a solution to the privacy question. I'm not sure that it really is, but I think we can do a lot to compute identity from depth images and even gait and that sort of thing. So it's a really tough question. I don't have great answers for that, but I think in a public place, at least, like let's say if you deploy this in a doctor's office, I think it kind of makes sense that you would not have necessarily an expectation to privacy as you would in your own home.
That makes
sense.
Thank you. Yeah. All right. Thank you, Andy. All right. We also have some questions for the next paper. So these are some questions for Alan. Oh, sorry. Yeah. No, these are some questions for Alan. So there was the question about different body sizes, if you've thought about that as well. And I'm actually thinking as well about different hand sizes. Have you considered that?
Yeah, we did think about that. And in the experiment, we did collect those information, like we measure the finger length and measure the palm length, palm size. But during the analysis, because there's too many factors of the finger length and there's just too many different sizes. So in the analysis, we cannot really run the analysis for the performance or for the preference. But so in this work, we more focus on what this site input area can do. But that definitely will be the interesting future work to analysis how small size of hands will affect to the reachability.
Okay, perfect. Another question that came up, so sorry, the previous question was from Joaquim George. Another question from Inigo Escuria was, what about involuntary activations? Because you tend to use that side to actually grab your phone, right? So how does that work? And have you thought about that?
Yeah, that is a really tough question. And it's kind of like in our limitation. Like in our experiment, in our study, we just measure the area that is on the topper of the phone. So that's likely people now grasp their phone in those areas. But we think about the involuntary activations. It's kind of like in the previous work, like the Infinite Touch one, they use the one-dimensional capacity sensor on three sides of phone, and they can use the capacity sensing to detect the grasping postures. So we kind of think if we can use if we can detect the grasping posture in the future, then we can use that to detect the involuntary activation.
Right. And another question for you is, what about the learning curve for the users for this mobile site input?
Yeah. So for the tapping and the flicking experiment, we didn't really detect the learning curve here. Like the learning time is the time to perform those gestures is quite the same. So I think people probably just really naive to tap on the side.
All right. Yeah. This was actually a question by Adam. I think so. I hope that answered your question. All right. We have a few more questions for our last presenter as well, for Sohei. So there's a question about related work. So how does your work on guided tracing compare with Pedro Lopez's work on muscle electrostimulation for transferring drawings from CAD to paper?
Yeah, actually, that's a very great question. I really like the work. It's called the Muscle Plotter. And for those who haven't seen it and are interested in pen and paper interaction, I highly recommend it. One thing that I would say is that the Pedro Lopez work's Muscle Plotter basically provides stimuli, and it's only 1.5 3D, which means that basically it cannot guide you in a 2D environment. So what it requires you is like you have to start the drawing with your own force, and then in that way it sort of like provides you with their wrist twist, something like that, and provides you with that. So it's not a full 2D. In another point, I would also need to say that I haven't seen that Pedro has done work on control sharing with the electricity simulator, at least for other work. I haven't seen that there, like, and I'm curious to see if it is possible to do control sharing actually with the electricity simulator of muscles.
All right. And next question is about using this to learn how to sketch. And this is a question from Catarina Fidalgo, and she's asking, did you have the opportunity to experiment with kids? And do you think it will be a good tool for kids to learn how to sketch, or would it actually hinder the creative process?
That's also a very good point. I can answer to these questions in 3 levels. First, one thing that we learned by providing haptic assistance to the learners, either with the sketching or for handwriting, we find out that basically we don't need just guidance. Even resistance to the hand of the user sometimes is very important. So if the users fight against the force feedback, they might even learn better. So that's from a technical or technology of how to use the device. Another point is that so there is also like a notion of quality in drawing. And what do we mean by that? What do we mean when we say like this drawing has a higher quality, and like how can we judge it? There are 2 different concepts that I've seen that literature came up with. One is realistically proportioned. So one thing that we can say is that, yeah, we do not prevent users from fluidly express their idea, but we might help them to keep the proportions right, and keep proportions right, like to the, I would say, versus the realistic that we see in the nature. The other one is that perceptual features. So what differs a donkey from a horse? So what are those subtle differences that we have to maintain in our design? And that could be a collaboration between the system, machine learning, and like when a person is doodle. And then one other thing that I would also say is the fluidity of expression. So like we have seen that when you start putting the pen down and there is a force under your hand, like the idea is coming out. And we actually didn't want to prevent users. That's why we invented this control sharing, that like we do not force the users to do something. So if you want to take control, just put more pressure on the tip, and control is all yours. So do whatever creative way. But if you are hesitant, like how to draw this rectangle or circle or something, then the pen will guide you. Yeah.
All right, excellent. I also have another just quick follow-up question. I was wondering about the mixed initiative system kind of that you have, where you know, in some ways you have some guidance and you can actually work against it. Do you have any thoughts on like how you can expand on that, or like how that control aspect could be explored even more?
So you mean that so hindering or so we have like one of the things that our system is capable of is providing 2 different types of constraint. One is preventing users. So for example, you can imagine that there's a channel, so which doesn't let you go out of that channel. And there is the other one which drags you along the line. And what our system can actually do is that it can goes into both of these modes. So it can guide you or it can prevent you. And as well as it's control sharing. So you can think of a ruler that becomes soft and soft. So it's like becoming a rope, and you pull on it. There is still something, but it's not as rigid of a ruler.
All right, perfect. Well, we're almost out of time. I actually have one really quick question for Adam, and I hope it is also a quick answer. I was wondering if you thought about the impact of the device that you used for your study.
Impact as in magically compared to HoloLens, or AR compared to VR?
For instance, yeah, and field of view and things like that.
Yeah, we had a pretty small field of view and kept things directly in the center. I think that the impact of AR versus VR manifested in a lot of the hand shapes that we found. I'm not sure if we would have found huge differences if we used a different optical see-through display.
All right, perfect. Thanks so much. And with this, we're at the end of the session, and I would like to thank all the speakers. Again, this was a really great session. Lots of great talks, great discussion. Thanks everyone for adding their questions as well. So thank you so much, and see you next in the break and then in the demos.